So there's this new quantity called angular momentum that we haven't learned about yet, and we're about to be introduced to it. And one thing that I want to point out before we get started is that angular momentum, and I made this point in the general introduction to rotation video a couple of weeks ago, rotational kinetic energy is plain old vanilla kinetic energy. It's just a more convenient way to write it when you have something that's rotating on a fixed axis or even rolling without slipping. This is different. Angular momentum is not the same as linear momentum. It's a different quantity, it has different units, and there's a whole different conservation law for a conservation of angular momentum, which is, it can be the case that you have an event where angular momentum is conserved and linear momentum isn't, for instance. So it's a brand new quantity, so please don't implicitly make that comparison. So what is it? I'm actually going to teach this to you kind of backwards, because I'm going to start off with this sort of intuitive approach. So I remind you of plain old linear momentum. P equals mv, and P is a vector, and v is a vector, m is a scalar. And that's the linear momentum of a thing of mass m, and its center of mass is moving with velocity v, and it has momentum p in the same direction as linear velocity v. I will state now without proof, I can call this a definition, that if you have a rotating object, so if you have a round thing, this is like the 9,000th round thing we've drawn, and so it could be a disk, it could be a frisbee, and it's rotating with an angular velocity omega, which we just learned in the last video. In this case, it would actually be an angular velocity just out of the board. It has an angular momentum, which is L equals I omega. And this is very analogous to the linear momentum formula, because we have on the right-hand side a term here, which is a scalar quantity, mass in the case of linear momentum, rotational inertia, or moment of inertia in the case of angular momentum. And it is a quantity that describes the resistance an object has to changing its motion, to changing this stuff. Something with a lot of mass, it's hard to change its velocity. Something with a large moment of inertia, it's hard to change its angular velocity. Then we have this quantity, which is a vector, angular velocity is a vector, which describes the rate at which something's moving, either translating or rotating. And finally, we have this new quantity, which is the product of those two, linear momentum or vector angular momentum, in the second equation. So this helps it be easier to remember this formula, if you will, that is very analogous to the linear momentum formula, but again, this is a different quantity. If, just for the sake of figuring out units and stuff, if you have something which has a rotational, an angular, moment of inertia, trying to change it, moment of inertia of 6 kilogram meters squared, I'm just making up some numbers, and an angular velocity with a magnitude of 9 radians per second, you're going to end up with, this is just to illustrate what the units are, you're going to end up with something with an angular momentum of 54, don't care about the number. We get kilogram meters squared per second. So this is just to illustrate that it has different units from linear momentum, as I've said 1,000 times. Units for linear momentum are kilogram meter per second. This is kilogram meters squared per second. So there's that. Okay. Now I will also mention right now, as a bit of foreshadowing, that in the absence of external torques, there's a law of conservation of angular momentum, and there are lots of familiar examples of things where you apply this, and so if you have figure skaters or athletes who are rotating, spinning, and they pull their hands and arms in, they can make themselves spin faster. And what they're doing is they're reducing their moment of inertia by getting more mass close to the axis of rotation. The angular momentum stays constant, and so this quantity, the angular velocity, goes up to compensate. So I gets smaller, omega gets bigger, and in that way someone can pull their arms and legs in as they're rotating and spin faster and faster, like a figure skater in a spin. And that has to do with angular momentum. We're going to come back to that in more detail in a little bit. What I want to do now is, so this is, I hope, not necessarily intuitive, but, not that difficult because it's sort of analogous to linear momentum. And it kind of makes sense that something rotating has angular momentum. But now what I want to do is give you the more formal definition of angular momentum. And I'm actually going to give it to you as a cross product, amazingly enough. And I'm going to give it to you in a less intuitive situation. What I'm going to say is this. I have a particle of mass m. And it's not rotating. First of all, it has no, it's a point mass, it's a particle. But it's not on a turntable, so it's not rotating around a turntable. It's just translating through space. And so I'm going to give it a velocity v, which is a vector. And I'm going to put it in a coordinate system. I think I'll make my coordinate system x, y, and I have an origin of the coordinate system, which is going to be my reference point. And at this point in time, I might note that the position of this object relative to the origin is this vector r vector, which is from the reference point or origin to the present position of this mass m. This is all fun stuff. Well, now what I'm going to do is this. I'm going to define the angular momentum of this particle moving in a straight line, not rotating, moving in a straight line, and I'm going to define the angular momentum of this particle vector as the cross product of r cross p, where p is the linear momentum of this vector. This can also be written, if you want to, and I do right now, as r cross, instead of p, I can write the equation for p, which is m times v. And I can pull out that scalar m and throw it out front if I want to. And this is m times r cross v. So either of these forms is a fine way of defining the angular momentum of a single point mass relative to a reference point, in this case the origin of my coordinate system. And so what does that give me in this case? It gives me the, and I'm not going to say a whole lot more about this to keep this short. It tells me that this particle has an angular momentum, and I would ask you to try to figure out the direction of that angular momentum vector by doing the appropriate right-hand rule that we learned in the previous video. And you should be able to come up with a direction. And I am going to, as you are figuring that out, I'm going to draw my z-axis because it's fun. And in my attempt at 3D perspective, my z-axis is kind of coming out of the board like this, my z-axis. And, okay, so what is the direction of that angular momentum vector? Remember, it is perpendicular to the plane created by these two vectors, v and r. And so now what I'm going to do is I'm going to move these vectors so I can put the v and r with a common origin. And this, of course, is angle phi, right here, the angle between them. And the direction of the angular momentum is found by the right-hand rule crossing r into v with your right fingers, and that leaves your thumb pointing into the board, into the screen, and it gives me an angular momentum vector, which I'll draw here in the negative z direction, L vector. For this particle, and now I'm going to put these back where they were, and so that is, put the particle in a slightly more realistic looking place. Okay, so that is the angular momentum vector is in the negative z direction if I have this particle moving in the positive x in the location shown. That's cool, I guess. It is what it is. And I don't know why I just moved that. And I think that's all I'm going to say about angular momentum for right now. Thank you very much.